Okay, so what did we talk about last time? So last time we did kind of this robust control story. It was a very quick sort of overview of an entire field that, dominated the controls community, for like 20 plus years. So if you're into this, just go check out some other stuff, there's a lot out there. And then we kind of talked through this minimax DDP algorithm as just a sort of a hint at like kind of, typical stuff that people talk about, like this kind of minimax style of approach is very, very common in the robust control literature. And that was just kind of in the context of DDP, which is something we've done in class before. So not too big of a delta away from stuff you've hopefully seen. So that's the robust story. So now we're going to kind of switch gears. There's going to be one more sort of, there's going to be an RL sort of topic lecture next week, but now we're going to sort of mostly start talking about these case studies. So we're going to do that starting now. There'll be kind of 3 of these and then the RL lecture, and that'll kind of be it. So we'll start off today with one of my favorite things. And one of the coolest things to happen in control in recent years, we're going to talk about the rocket soft landing problem. We're going to talk about how to land your spaceship. Super cool stuff. And as a sort of fun intro to this and to sort of, get everyone psyched up, we're going to watch some fun YouTube videos. So first off, this is the paper we're going to go. This is a paper from 2013. This is basically the topic of today's lecture. I'm going to walk you through this paper. This came out in 2013. The lead author here, Bechet Achikmeshe. So these guys were all working at JPL at the time. So this is a 10-year-old paper now. Modern classic. You should totally go check it out. Huge deal. Again, like this is one of the biggest things that happened in like aerospace for sure, and controls generally probably in the last decade. Bechet Achikmeshe, awesome guy. Formerly of JPL. All these guys were at JPL at the time. He's now a professor at University of Washington. His lab is, one of the, heavy hitter controls labs. So if you go to ICRA, you'll frequently see his lab represented there doing all kinds of crazy stuff with drones and stuff. John Carson, who still works at NASA, and then Lars Blackmore, who was poached by SpaceX. And he's been running SpaceX's, rocket landing stuff for the last several years. So these people are all heavy hitters and super cool. This paper is awesome. So we'll walk you through the paper, but I highly recommend checking it out. Like it's super good stuff. It's definitely changed the game, and how people think about this area, and it has had a big practical impact. So yeah, paper is cool. Check out paper. So here's what we're doing, right? So we'll look at a few examples of this. So this is obviously the SpaceX version of this. I think this is the last, major Starship test. They're gearing up to do another test flight of this, but this is the power descent phase, right? So this is coming down. They're going to light the rocket back up.
And we have ignition.
And this.
Starship heading back to the landing zone.
So yeah, precision rocket landing, insanely cool. And you guys have all seen these before, right? You've seen the landing on the barges in the ocean, like just insane, right? So cool. Okay, so that's obviously, so Lars Blackmore of that paper I just showed you, he's been running the group at SpaceX. He's been doing this for the last several years. And then on the NASA side of this, this is also how we've been landing on Mars the last couple times. So this is the cartoon version. There's a little more clarity here, but so it's parachute, right? Throw off the aeroshell. And then this is the part we're talking about. Light the rockets up. This is called power descent, right? So this thing flies down on these missions. This is Perseverance. They actually flew what's called terrain relative navigation, so vision-based navigation that was actually originally developed at CMU. And the guys who do this at JPL came out of CMU, so there's some awesome local connections to this stuff. And yeah, so the controller we're talking about is what's flying this thing right now. And then Sky Crane, right? It's insane. And then right now what they do is they cut the lines, and then this guy does this sort of divert maneuver. They basically fly it off sideways and crash it several hundred meters away so that they're sure it's not going to like get in the way of the rover. So that's that. That's and then the really insane thing is on Perseverance, they actually had 4K live video feed of this thing. So that was animation. This is the real video from this thing when it landed. So this is starting about 1 kilometer off the surface.
Here on safety Bravo.
And you can hear in the background.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters.
So this is all
off the
really
surface
fast. This
of
is like
ours.
300 meters up when they turn this thing on, right? And
We have started our constant velocity
so you can see, like,
accordion,
that's
which
how
means
quick
we
it's
are
flying.
conducting
Looks
the
like
sky
dust coming
crane,
out from the rockets.
about to conduct the sky crane maneuver.
And then sky crane.
Sky crane maneuver has started. About 20 meters off the surface.
So yeah, that's the, the lander up there. You can see the view looking up from the lander, and then they cut the lines and they do this divert maneuver. Crash the descent stage.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars,
That's it.
ready to begin seeking the sands of past life.
Actually, yeah, one of my good buddies from undergrad is in that, like, just to the left in that shot. He runs like EL stuff there. Yeah. Anyway, super cool.
So fat.
All of
Brendan,
that
you're not fat. It's the shirt.
Okay. You don't want t-shirt ads. Go away. So yeah, all of that is autonomous. One of the big reasons is that there's a huge amount of light time delay. So the RF signal propagation time from Mars to Earth is like minutes. So you absolutely can't close a control loop right around that. You can't do anything. There's too much delay. So the whole thing there, like by the time you get that video feed on Earth, it's already done, right? It's already happened, which is kind of nuts to think about. So it's totally autonomous, vision-based navigation, the control stuff we're going to talk about, right? All of it has to work perfectly, right? Which is kind of intense. One of the big reasons this is necessary, and this whole terrain relative navigation thing is necessary, is actually the what's called guidance part of this, where it's like fireball style coming through the atmosphere. The targeting and everything for that is quite bad. So what they call the landing ellipse, where this thing comes down, it's about 10 kilometers or so across. Like they can't really pinpoint anything. So when the parachute pops, they can only say where they are to about within 10 kilometers. So that's where the vision stuff comes in. They're not trying to find a spot on Mars with the vision system. They're really just trying to steer around boulders and make sure they don't land in a really bad spot that's like, steep or littered with boulders or whatever. So that's what's happening at that last final stage. Anyway, hopefully that got you all hyped up. It's awesome. All right. Yeah, so let's kind of like, I'll like start talking through some of this stuff, but feel free to, speak up. So, okay, the problem here is called the rocket soft landing problem. And this has a long history in the aerospace community with lots of different algorithms been developed going way back, go all the way back to like Apollo in the 60s, right? So people have been thinking about this for a long time. And the gist of it is you want to go from some initial state x naught to some final position, say r final, with zero velocity. That part's important. So z final, so zero height and zero final velocity, right? So parsing that out, right? Landing means that your z final is 0, and soft is the v final equals 0 part, right? That's important. And then generally what we do, so those are kind of, the constraints, terminal conditions or whatever. And usually the objective here, the cost function, is something like minimize some combination of fuel consumption and landing position error. That's sort of usually what happens.
Question.
Yeah.
So when like SpaceX, for example, is landing on like the drone ships, those are like moving.
Yes.
So like your final condition for your final state be what the state of the,
Yeah, so they actually, I think they try to do an extremely good job of keeping those drone ships in position. So like the SpaceX stuff all uses GPS, high-end GPS, and they like really know where that drone ship is and where the rocket is at all times. I'm not sure if they're actively closing a loop around the drone position or if they're just using thrusters on the ship to keep it super precisely positioned. So I don't know the answer to that. I do know they're using, basically with GPS, you can get down to like sort of meter level accuracy everywhere. So I don't know if they can maintain the drone ship position to within a meter or two, but I think they kind of try to do that. I think it's part of the deal. So I don't know that they're like forwarding the updated ship positions to the rocket. I think they're just trying to keep the ship position super tightly controlled on the ship.
but if the ship is like moving up.
Yeah. So I think basically what they do is they don't try to do this if the seas are super rough. I think that's what happens. I don't think they're like actively sort of updating things for that. It's just got to be robust to a certain amount of that. And if it's outside of whatever spec they can actually tolerate, they just don't do it. Cool. Okay. So that, and then, yeah, the other piece of this is respecting thrust limits and safety constraints. Okay, so yeah, examples of this we just kind of saw. So the NASA stuff, kind of recent Mars landing stuff. So the first version of this was Curiosity. The first sky crane, which was in 2012. And then you've got all the SpaceX stuff that everyone's seen also. So both the Falcon 9 stuff and the Starship stuff we just saw. And then the more recent Mars landing that we just saw, which was Perseverance. The cool new thing on Perseverance was the terrain relative navigation stuff. So that's 2021. And that let them land in more scary places, basically. Like prior to that, because of this like 10-kilometer uncertainty, they basically picked landing sites that were sort of very open plains without a lot of stuff to hit. But the TRN stuff lets them kind of land in sketchier places. So these are kind of cool recent examples of this stuff. And then there's sort of lots of tricks to make this stuff work in practice, which we'll talk about a little bit. All right, so any questions about any of that? All right. So what I'll do now is kind of outline the sort of the full control stack that at a high level for one of these things. So how this tends to work is you have a position controller, which is kind of the piece we're going to talk about the most. This feeds in acceleration, like linear acceleration commands. So when I say position controller, this position controller is basically reasoning about the dynamics of the rocket as a point mass. And it's just doing kind of F equals ma stuff. And it's trying to figure out, acceleration commands on that point mass. So those, as far as the positions controller is concerned, it's got a point mass and its control inputs are accelerations subject to some constraints. Then this guy feeds into a lower level attitude control loop. And this thing is figuring out thrust and gimbal commands, basically to achieve a desired pointing angle that results in the linear accelerations that you want. So this guy spits out something like T theta, say. So these would be thrust and gimbal. angle. This is linear acceleration. Then this sort of actually goes and runs on the rocket. Then, you know, down here you've got your usual state estimation stuff. And this is feeding attitude state stuff. So your sort of quaternion and angular rate stuff into the attitude controller, and it's feeding your positions into your position controller. So this is like your R, V. So all right. Any questions about that setup? We'll talk through some of what's in here. So this is kind of actually one of the amazing things about this, which is what we're going to talk about. At least the position, the way we've decoupled this, the position control problem, which is what we're going to talk about now, is convex, which is awesome, which means you really don't need a reference. You can solve this thing from scratch super quickly and super reliably online. And that's why this paper is like such a game changer. They figured out this like convex formulation of the problem so that essentially you can like just keep resolving this thing online at real-time rates, and you don't need to like have some really nice offline reference that you've pre-computed, which is cool. Okay, so some additional sort of info on this whole thing. So on the state estimation side, the sort of SpaceX version of this on Earth, you basically can get away with using GPS and an IMU for all this stuff. You know, with your typical Kalman filter kind of approaches. And this can be, if you do a good job of this, you can get like GPS plus an IMU, you can get down to like sub-meter accuracy with a good like filter implementation. So this can be extremely good. So yeah, you can get the position errors kind of down to that meter level, and you can get the velocity errors down even more, like way less than 1 centimeter per second. And attitude wise, you can similarly do a really good job. It's like less than a degree. And this is really kind of on the state estimation side, that's all you need. So this is how you do the land on the drone ship sort of thing, right? The story for like the Mars stuff is way harder. Obviously, there's no GPS around Mars. So what they have in terms of sensors, so they have an IMU, they have extremely high grade IMUs. They actually integrate so they take the like orbital position computed via the deep space network for the orbiting vehicle in space. Once you hit the atmosphere and you do the fireball thing, you lose that link. So they actually end up dead reckoning with an IMU all the way down during the entry phase. The integrated up position and attitude errors after doing that for like several minutes are surprisingly small, but they're pretty huge. So your position uncertainties are going to be kilometers. Your attitude uncertainties maybe, you know, degree or two after dead reckoning for like 7 minutes during the entry phase. So let's see. So that's what happens. So they have the IMU, they have a radar altimeter. So you know how high you are above the ground, which is the most important thing. And then, yeah, recently there's now vision in the mix. The vision system's pretty good on these things. So they, I think they quote like roughly 30 meter accuracy. But what they're using that for is really just this sort of avoiding boulders problem. As you kind of saw right in the video, they basically turn all this stuff on like you know, a few hundred meters above the ground. So at that point, you're not like, you know, flying a kilometer to get to some point on the map. You're just looking straight underneath you and trying to find a smooth place that doesn't have a lot of rocks to touch down. Okay, cool. So that's the state estimation story. And then the other thing to talk about is kind of this whole decoupling of the controller. Has anyone seen anything like this before? Yeah, I heard the drone thing. So has anyone done drone stuff with kind of the standard PX4 style drone controllers? They all do this. Does anyone know why that's a thing? It's like decoupling of a position loop and an attitude loop. It's super common on drones. So the gist of why this is a thing is typically, this is definitely true of drones, it's true here too. The attitude dynamics are usually fast and unstable. So they have to be stabilized at a high rate, whereas the position kind of dynamics can be much, much slower. And so what this lets you do is kind of run this attitude tracking loop really fast with some low-level simple controller. And then the higher level position controller can run a lot slower and potentially be much more sophisticated. So here what that means is, you know, this attitude controller is basically stabilizing the vehicle and make sure it doesn't like flip over and crash. That has to run really fast, relatively speaking, but it can also be a really simple controller. And the standard there is actually to use like very old school linear feedback, like hand-tuned pole placement style, like PID style stuff. And that loop runs fast, whereas this position controller can be much more sophisticated and can run at much lower rates. So here, that's the attitude controller is some kind of like hand-tuned, you know, frequency domain, you know, linear thing. The position controller is this like very sophisticated convex optimization thing that's solving for a full like landing trajectory all the time. So let's write that down. So you've got this higher level position controller. This uses a point mass model. And reasons about safety stuff, thrust limits, and fuel constraints. And this thing generates a sort of acceleration commands, basically. And this controller might run at like single-digit hertz in a typical application. It doesn't have to go any faster, basically. And then this low-level attitude controller is reasoning about obviously the attitude stuff, but also part of this is, which we'll talk about a little bit more, is that turns out for rockets, certainly in the SpaceX scenario, these things are really big. And they tend to have, they're built to be, they're very big and they're built to be as light as possible. So part of the story there is they have pretty low frequency flexible modes. Like it's unavoidable, right? It's big and it's lightweight. And so it turns out you actually have to think about that in the controller. Otherwise you end up shaking the rocket apart. And this is actually a real thing that happened in the early days of like the US space program. I'm sure it happened in the Soviet Union too, but they didn't, you know, put that on the news back then. So like, but yeah, all these, like you'll see like these videos from the late 50s and early 60s in the early days of the space program, just like these rockets blowing up all the time. And a big part of that was these kind of instabilities that were created when you would hit a flexible mode in the structure of the rocket, and you end up with a resonance where like the feedback controller is trying to like, essentially it sees the flex as an error. And you, this shows up all the time, by the way. If you have any kind of resonance in your system and it's modeled as a rigid body, the controller will basically start trying to fight the resonant mode, and you create a positive feedback loop, and it just blows up. It just shakes the thing apart. So that's a real thing. And another thing that shows up is fluid slosh. So yeah, there's a bunch of like, this is getting at like, we can talk about these things as idealized rigid bodies, which we do all the time. Very frequently though, when you go to a real system, there's these like non-rigid effects that show up that will start to matter. Here, this is flexible stuff and fluid slosh that are highly non-trivial, but this does show up in all kinds of applications, like shows up in legged robots too, like, yeah, all kinds of things. In drone land, the typical gotchas are aerodynamic stuff that you don't model, right? You model this thing as a rigid body, but if you actually try to go fly it around aggressively, there's like lift and drag going on and these things, that you're not really modeling. Okay, and this thing generates the actual thrust and gimbal commands for the rocket.
So if we decouple position from attitude and we only reason about the final position and speed and such and safety in the position controller, how do we keep the rocket from landing at an angle and then falling over?
Yeah, so we'll get at this. So basically, the position controller, right? That's basically MPC. It's even like it's solving a full trajectory optimization problem from current state to landing and resolving it constantly. And it's got a bunch of constraints in it. Notice the word safety in there and all this kind of stuff. So essentially what happens, we're going to talk through this. The main sort of novel trick in this paper is how to reason about these sort of thrust limit constraints. And the way those things basically manifest themselves as conic constraints. You end up basically saying, I'm willing to produce thrust within this thrust cone. And that thrust cone kind of directly corresponds to how far away, over you're willing to tilt the rocket. So by putting these thrust cone constraints in here, you're like sort of getting at that.
You're sort of doing implicitly instead of explicitly reasoning about, don't be at 10-degree angles.
Yeah, I guess like, so the thrust cone constraint stuff it's basically always conservative. And like, there's kind of no way you can satisfy that thrust cone constraint with the rocket sort of like tilted over.
Right, so
The gimbal's only a couple degrees, right? So like by kind of baking in a few degree thrust cone constraint, like there's just no way if you're commanding like, the thrust vector, I can only point, say plus minus 10 degrees or something like this. You just can't have the rocket sort of tilted over in that situation, right? There's also a lot more sort of safety flavored stuff that gets put into these things. So there's usually in typical implementations, they also have what's called a glide slope constraint, which gets at the sort of stuff you're talking about as well. It's basically puts limits on the like approach angle to the ground. So they're sort of not allowed to, it basically restricts them to flying towards the goal landing site within some cone. So they don't sort of, if you naively set this problem up, it's very easy to get things that like do this and like go through the ground or whatever, right? So they tend to do this sort of glide slope constraint as well that forces things to be well behaved and sort of come in almost vertically to track, right? So this thing tracks the accelerations. And these on a big rocket, these might run at sort of like tens of hertz. And that really depends on the sort of inertias and things like this of the rocket. Like the bigger the vehicle, the slower the dynamics, the slower this thing has to run. It's kind of the idea. Okay, questions about that? I don't know what SpaceX uses. I think the JPL stuff is RAD 750, which is, if anyone knows about like computers used in space flight, these are the like really radiation hardened stuff that like, for example, the Mars stuff uses, these NASA missions use, where it's like absolutely safety critical. They run PowerPC 750s, which are like a sort of late 90s, early 2000s vintage equivalent to what was in a G3 Mac. So if you had like one of those colorful iMacs as a kid, it's the CPU from one of those from like circa 2000. And they're, I think they're clocked around 200 megahertz. So they're like relatively crap and, like 20-year-old, processor technology. The reason is they're like built on like very old process nodes they're basically like made with like super beefy traces and all this stuff, and they have all this stuff engineered into them to be super radiation hardened, so that like if they get hit by, you know, radiation, cosmic rays, et cetera, high energy particles, they won't fail. And they can tolerate very, very high radiation doses and still work. So that's sort of, and in like the uber safety critical stuff, it's also common to have 3 of them running the same code simultaneously and then voting, so that if something gets messed up, you do a best 2 out of 3 kind of thing. This is real. It's like, that's actually how the space shuttle computers worked. I don't know if the Mars landers did that, but did they do this also? Yeah. So this is very common. Yeah, the only exception to this sort of like insanely, you know, overbuilt, super old school, rad hard CPU stuff is the Mars helicopter stuff. They've actually backed off on this. I don't know if you guys probably have heard of this, but the Mars helicopter used a Snapdragon. So it's like smartphone chips, and they basically were willing to tolerate a lot more risk on that than like on the lander. The stakes were lower, but yeah. So people do fly more modern sort of, you know, consumer grade stuff, but it's not in these kind of very safety critical situations.
Basically, like wind and all those disturbances are not aggressively modeled, and that all implicitly handled by low level.
Yeah, I mean, these things, you know, that all that is just disturbances that will get mopped up mostly in that attitude loop. Yeah.
Low level controllers are always very controlled.
They're not always, I would say, but in this context, in these situations, everything I know of, like from industry, is all they're basically like very, very dialed, hand-tuned, like pole placement style, like old school CISO frequency domain control designs. Like these things they're not just PID, they're usually like very complicated, you know, things that have been hand-tuned using like Bodie-Nyquist type ideas and like extensively Monte Carloed. Because it's, you know, they're also doing things like, so this like, you know, say flexible mode stuff, right? The way you get at that in like one of these controllers, you might start with something like a PID controller, but then you're like, oh, well, the rocket has this 8 Hertz bending mode. And if I have any frequency content in my controller around 8 Hertz, it's going to excite that bending mode and shake my rocket apart. So what do? You go in the frequency domain and you put a notch filter in the controller around that 8 Hertz bending mode. So this is the kind of stuff that happens. So like if there's any, say, structural bending frequencies within the controller bandwidth, like if I'm running this controller at, say, I don't know, 20 Hertz, right? Well, if there's any bending modes within that 20 Hertz bandwidth, you end up going and having a notch filter so that you're really sure the controller doesn't, you know, shake the rocket at the wrong frequency. So this kind of stuff happens, right?
Based on what should I say is the high level?
Oh, you mean just like, what do you call these things? I would say here, I don't know. I mean, these are just semantics, right? These are just names I'm attaching to these things. Here, though, like the reason I call these high and low level, I guess is the low level thing is actually the thing that's generating the actuator commands, and is running sort of closer to the hardware, right? At a higher rate. The high level controller is using a much more abstract model, and it's reasoning about these like sort of, I would say higher level things, right? Safety constraints, blah, blah, blah. It's reasoning about higher level stuff. It's running slower and it's using a simpler model. Whereas the attitude controller is running really fast and it's the thing that's actually commanding the actuators, right? I don't know. But again, these are just names that, you know, whatever. Okay, so that's that. Any questions about that? Cool. Okay, so then a little bit about rocket dynamics. So how do we model these things? They essentially, like this position controller stuff that we're talking about, this is a really simple rigid body model. And let me draw my horrible cartoon rocket. So you have like your engine, whatever. You've got some thrust vector. Let's say you've got your CG somewhere over here. You've got some distance L between the engine and the CG. And you also have, I'm going to draw a terrible picture of like a fuel tank in here, something like this. So rigid body model, You've got sort of Newton-Euler type dynamics. So this might be, you know, minus G plus T over M. So you've got gravity and you've got thrust, right? That's F equals ma for a point mass. The interesting thing on these rockets that is like maybe you haven't seen before in robotics is that you have time varying mass. This actually ends up mattering a whole lot. So rockets are typically like 80% plus fuel by mass. So as you burn fuel, the mass changes a lot. So that's something you got to reason about. So this is, let's say, point mass dynamics. This is fuel burn dynamics. And it's just proportional thrust, right? Kind of makes sense. And then you'll also have your sort of attitude stuff. Euler's equation. So this stuff up here, this is the stuff in the position controller. And this is that slower loop. This guy is the attitude control. And is relatively fast. Okay, let's see what to say about this. So yeah, fuel is a huge chunk of the mass.
What is J?
Oh, the inertia. This is Euler's equation, which we've seen a couple times. Same. This is exactly the same as a drone modulo the fuel burn stuff, right? Inertia, angular velocity, right? Torque.
What's the dynamics for J?
Yeah, so that is also time varying, right? Is that what you're getting at as a function of mass, right? So if I were to build a model-based attitude controller, I would probably care about that. But here, as we kind of were getting at, these attitude control loops are typically very old school, like hand-tuned, essentially like PID style controllers. So they're not actually model-based and they're not using a model internally in the controller. And the way those get designed is extensive Monte Carlo, like hand tuning, you know, maybe some flight data, hand tune the gains some more. That's like how that stuff gets done.
Have like some gain scheduling as a function of like.
Yeah, I mean, I don't think they actually do. So you might do that. I think so. Again, I don't know. Don't quote me on this. Like, but my impression is that they are not doing gain scheduling on those attitude control loops. I think they just tune them up, and they're designed to be super robust, right? And there's all kinds of weird stuff they try to account for. So I think they basically just tune those things up and get them to be good enough that they don't have to do that. But again, don't quote me on it. It's entirely possible that people are doing some gain scheduling. I don't know. But that part is not model-based, right? It's this hand-tuned thing. The top part is model-based, and that model is what's going to go into this charge-opt formulation that we're going to talk about. So lots of the mass is fuel. And like total mass sort of therefore can change by like, you know, 2 to 5x, say, during a landing. So you have to account for this.
How like practically often is the mass decrease actually done?
It's close enough to that works. I think that's basically, it's proportional to thrust, right? Like the thrust kind of gives you this burn rate. So I mean, that's not an unreasonable model, I would say. Yeah. Okay, so that's mass stuff. The other thing that's worth talking about is fluid slosh. This is one of the harder, weirder aspects of this problem. It's highly nonlinear. So if you don't know what I'm talking about here, it's like your partially filled fuel tank, right? As you burn fuel down, like you got this tank, it's half empty, half full of liquid. The liquid mass is comparable to the whole mass of the rocket or whatever. It's a huge chunk of the mass. And as you move this thing around, that fluid's sloshing around in the tank back and forth, inducing very weird, highly nonlinear, hard to model dynamics. So this is kind of fun. Does anyone know or heard about how this actually gets handled in these sort of aerospace scenarios, like the standard model for this in rocket land, where they simulate this stuff and try to design controllers? It's kind of fun. If I told you what that looked like, how would you think, if you had to come up with a really simple model of that fluid slosh stuff? Anyone have any thoughts on how you might do it? That's pretty good. Yeah, the mass on spring. Anyone else have? So it turns out like a really good model of this, the mass on the spring is not unreasonable, but a slightly better one is a pendulum. So you basically model this as like a pendulum inside the mounted inside the rocket with like time varying mass and length perhaps, right? And that gets you the essential sort of back and forth sloshing dynamics. The reason it's a little better than the mass spring is that as you vary thrust, right, like the effective gravity is changing, right? Mm-hmm. Whereas the spring mass thing is sort of you could probably get at it too, but the pendulum model is a little closer to the right answer. Anyway, kind of funny. So so this is the picture, right? And data drawing. So you have this pendulum with a length and a mass that you fit to data. So that tends to be surprisingly, it at least gets it in the ballpark, so that if you design a robust controller that's robust across a range of L and M, parameters for that pendulum, it's probably going to work. That's sort of the gist of how this gets done. And this is, I would say at a high level, like, from a sort of philosophical perspective, this is like, philosophically, this is how we go at, modeling in classical model-based control. Like, this is the kind of stuff we do all the time, right? It's like you try to come up with the dumbest, simplest model that captures like the qualitative behavior and that tends to be good enough for doing control design, right? You need something that's qualitatively capturing what's going on. It doesn't have to exactly match, right? And then it just has to be good enough to get at the sort of phenomena. And then you count on the feedback controller to like sort of pick up the slop, right? So you don't need a perfect model. You just need to capture the relevant, behaviors, right? So pendulum for fluid slosh. And then the other thing that shows up here a lot that we kind of talked about is flexible modes. This is a big deal. So rockets are built to be very light. And they're big. So that kind of all implies that they are not stiff and therefore have low frequency bending modes. So rather than try to make some complicated flexible model of the structure, which you could do, right? You could do FEA on this thing and come up with some modal model or whatever. That is not typical. People definitely do that analysis, but they're not going to build some complicated modal whatever model to use in the controller, right? It's too complicated to reason about. The state's too big, blah, blah, blah. So instead what they do is basically maybe do some of that analysis, maybe collect some data, and then they go to the controller, again, doing this frequency domain stuff for the attitude controller, and just add notch filters in all the right spots to make sure they're not hitting those modes. So yeah, typically I would say, all right, your first bending mode on something like this is maybe going to be in the single digit hertz range on a big rocket, which is very low, right? These things are floppy. And so you can basically just go add notch filters. Anyone have any thoughts on how you might do this with, like, say, LQR or MPC? Yeah, how?
Estimate the frequency of there's something that like when you do like optimization for strength on those on that frequency.
Yeah, so you can do stuff like this. So there's, yeah,
Maybe a four crossing.
yeah. So now you're sort of getting at it. So there's a couple ways to get it. So one way, right, you could build a complicated model with the flexible dynamics and linearize it and throw that in your LQR controller and penalize like the, states associated with those bending modes. That'd be one way. That's perfectly reasonable, but it's going to get complicated, right? And kind of messy. So if you want to go with this kind of old school frequency notch filtering approach, the way to get at this is actually you can augment the state in your LQR controller with a filter, right? So remember, right, you can write down a, say, a bandpass filter as a state space model. Maybe if you're not E, you haven't seen this stuff, but like you can write down a notch, like basically the sort of notch filter thing that you would do, right? In the frequency domain, you can write that down in the time domain as a filter. You can add a state to your controller, and then you can penalize it, which is basically doing what we're talking about. Right? It's basically this thing that would like effectively filter your control signal and pull out the content in the U of t at that frequency. You end up having that be a state, and then you can penalize that state in the Actuator. So that lets you basically design a K matrix now that like gets at the same thing this notch filtering stuff would do.
That makes like say basically some things sort of uncontrollable because now you have like a direction where your control doesn't go into.
It's not, it turns out, like it is not uncontrollable. Like if you do this, you can definitely get this to happen. What you're doing is adding a state that is basically the energy content at a specific frequency in your control signal. So it's like by definition controllable. That makes sense. It's like literally what you're doing is bandpass filtering U of t and sticking like the energy in that band into a state. And so like you have control of that state almost by definition because it's literally just a filtered U. Makes sense? Anyway, I don't know. And aside, you can do the same thing with LQR with some tricks. Okay, cool. So there's flexible modes that are, usually poorly modeled. And then the last thing that obviously also shows up are aerodynamic forces. And sort of similarly to typical drone stuff, these are mostly ignored. And it turns out you can get away with ignoring them in lots of cases. If you wanted to, right, you could, for example, also like add velocity constraints in the position controller to make sure that the aerodynamic forces aren't big. The reason, by the way, like these tend to be, like the reason you can ignore them a lot of time in drone land also is that aerodynamic forces go like velocity squared. So if you're near hover, moving slow, like if you're moving slow, v squared's even slower. And so these forces don't actually get very big until you're moving a lot faster. But yeah, if you cared, you could do something like velocity constraints. Okay, so that stuff, and then yeah, so like, I mean, on Earth, we know pretty well. On Mars, near the surface, we also know pretty well. But yeah, there's still a huge amount of upper atmosphere on Mars. It's horrible. Like we know very little. And there's also like winds and stuff like this that are like really hard to, predict and characterize and stuff. So there's, even if you put something like this in there, it's probably going to get swamped by a brisk wind or something like that. So all that is to say, there's significant model uncertainty in all this stuff. And a very common like approach to this stuff is to use ideas from linear robust control theory, which we kind of talked about last time. So this H infinity stuff that we kind of mentioned last time is pretty sort of go-to stuff. for the like that attitude controller. Okay. Yeah, there's a MATLAB toolbox for it. Check it out. But if you've ever done like old school SISO, you know, Bodie Nyquist stuff, it's basically the new school modern multivariable generalization of those ideas. So you kind of sit there with something that looks like a Bodie plot and move around. Instead of poles and zeros, they end up being singular values of the closed loop system, but they have like almost the same interpretation. Kind of interesting. Anyway, okay, so that's that stuff. Are we cool with that stuff? Questions, thoughts? All right. So now we're going to actually get, so that's all sort of like high level, you know, background. Now we'll actually show you the punchline to the Lars Blackmore paper. Like how did those guys like, you know, come up with this thing that sort of enables this convex formulation and lets you solve this problem at real-time rates on your rocket. So a little background. So we've talked about convexity, right? Everyone kind of remembers that stuff from earlier in the course with convex MPC. We're now going to talk about this idea called convex relaxation, which is the key trick here, which is very, very clever and fun. So the basic idea is sometimes we can have a non-convex constraint that can be expressed as the boundary of a larger convex set. Does anyone think of an example of this? There's one classic one that shows up a lot. It's basically the one we're going to end up with, more or less. So maybe the most classic one is a sphere or a circle. So we'll draw like a circle, but it works for, you know, spheres in general. So let's say we have a constraint that like norm of X has to equal 1 or something like this, right? So if this is my original set, it's called S1, by the way. So this is X, you know, such that norm X equals 1, right? So let's say I have that constraint. That's clearly non-convex, right? If I pick 2 points on the circle and draw a line between them, that line is not on the circle, right? So this is non-convex. But what I can do, trivially, I can relax that to include the interior of the sphere as well. So we end up with a ball now. Right, and so this is our, say, enlarged set. We'll call this S2. So this guy is all X is such that norm X is less than or equal to 1, right? And sort of in fancy math notation, you would say S1, the set 1, which is the boundary set, right, is equal to this little funky differential symbol, which means boundary of S2. That's like a, I don't know, weird math notation for saying S1 equals the boundary of S2, right? Everyone cool with that? Cool. So, right, sphere, if it's just talking about the shell, right, or whatever, the boundary, that is a non-convex set. If I relax it from an equality to an inequality, though, and I include the interior, now that's clearly a convex set. Pick any 2 points, blah, 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 you get the idea. Cool. Okay, so let's see. If I do this trick in my problem and replace the original constraint with the larger one that's convex, this is called a convex relaxation. And in general, right, the relaxed problem is strictly easier than the original problem. If I do this and I solve this problem, in general, I might find some point in the interior here, right? And like when I say easier, I mean, it's generally easier to solve because convex things are easier to solve, but also I can probably find a lower objective value here I've made like the solution space bigger, right? So there's quite possibly some easier solution in the interior, some nicer lower cost solution in the interior. But it might not give me the solution to the original problem in general, right? There's nothing here. It's if I just do this as some random problem, I could come back with some point in the middle of the circle there that's not a valid solution to the original problem, right? So here's where it gets really interesting. So in general, right, I just do this and I try to plug this back into my problem and solve again. All bets are off. I might get something that's completely unusable for the original problem, but for some particularly nice problems, we can get lucky. And that's what's going to happen here, hint, hint. And it really comes down to the cost function in these situations. So if the cost function is particularly nice, we can actually still get the answer to the original problem by solving this relaxed problem. And we can guarantee that we get the original solution to the original problem with this relaxed problem, which is super slick. Anyone think of a situation where this would be true? Yeah, like what can you name it? Like, let's take this, for example. Can you like think of a cost function where I would always end up on the boundary?
Negative.
That's not a convex cost though. So that's a bad example.
This will try.
It's like a mountain.
Yeah, but that's non-convex too. So that would be a non-convex problem still. There's a really simple one. The simplest one you could write down actually pretty much. A linear objective. So it's literally like, C transpose X for some constant vector C, right? Minimize that. That just says, go as far as you can in the negative gradient direction or whatever, right? And so that's, it turns out like if you have a linear objective, the solution is, it's either unbounded, right? You'll go off to infinity in that direction, or you're just going to go to hit a boundary, right? So for linear objectives, which are usually the ones where this works out in practice, you just in general, linear objective, if it's got a feasible, i.e. not infinite solution, if it has a bounded solution, it's going to end up basically just going in the gradient direction or negative gradient direction if you're minimizing until you hit a boundary. So in this case, if I write, like, so I'll just write one of these down. In this case, right? So for example, if I have min C transpose X subject to norm X equals 1, I can relax this into norm X less than equal to 1, and I'll still get the exact solution to the original problem. And just intuitively looking at this, right? I've got my circle, I have my, say I've got, my vector C. The solution to this is going to be, go in the minus C direction as far as you can. That's how you minimize. And so I'll just go straight down here until I hit the boundary, right? And that's always going to be true, right? So in this case, this relaxation is what we call tight. So if you can prove that the solution to the relaxed problem always is going to end up on the boundary and therefore respect the original non-convex constraint, we call this a tight convex relaxation. Okay, everyone cool with those ideas? This is a big deal. I mean, there are other examples where this happens, right? But the most classic one is if you have a linear objective, you can almost always play this game. As long as the constraint that you had is the boundary of a convex set, you can basically always relax to include the interior. And because of this property of linear objectives, you can pretty much always do this. And this game, you can play this game in a lot of other situations that are pretty interesting and cool. Okay, cool. Everyone good with that idea? This is kind of a big idea. Like if you take a, sort of math or OR type optimization course on convex optimization, this is one of the big ideas that, you should learn about. Okay, cool. Convex relaxation, tightness. Okay, so now we're going to write down the actual rocket problem and sort of where this shows up. So convex relaxation of thrust constraints. By the way, the actual paper for this that I showed you, they call this a lossless convexification. I think they just made that term up. That is not the standard word in the optimization community. This is the standard word for this in optimization is tight relaxation. Okay, so in the rocket problem, here's what we've got. We've got a maximum thrust constraint. So that's pretty easy. And that's convex, right? So that's something like if I have a thrust vector in R3, this is basically the acceleration, right? In R3 on our point mass in that rocket problem. This constraint just looks like this: norm of thrust less than equal to some T max. So geometrically, this is just a ball in R3, right? And we've got our T in here. And this guy has radius T max, whatever. So this is a convex constraint. Everything's cool, no problem. By the way, what sort of optimization problem that we've seen already, does this fall into? Just this one. Is it a QP? SOCP, that's right, yeah. Okay, so we got that one. The next one is the gimbal angle or thrust angle constraint. So this one is looks sort of like this, right? So if I have some unit vector n, I can write this as n transpose t over norm t is less than or equal to some cos of maximum angle. So this looks like a cone. Where the sort of cone axis is that n. And then your t has to be inside here, right? So this is again, an SOCP constraint, right? To see that, I can move the norm t over to the right-hand side, and that's standard form SOCP constraint. So this is convex also. This is no problem. So we're mostly, things are looking good so far. So that's good. So here's where it breaks. So we also have, we talked about maximum thrust. It turns out rocket engines actually have a big deadband. They can usually only throttle plus or minus 10 or 20%. So there's, in addition to this maximum thrust constraint, there's also a minimum thrust constraint. You can't throttle it down super far. And that's where it gets nasty. So let's write this down. Rocket engine also has minimum thrust. Constraint once you turn it on. So yeah, you can't throttle below some T min. So you have something that looks like this. So geometrically, I'll just do the 2D version of this. It's a donut, right, in 2D. So you have your T min and T max, and this is your sort of feasible region, right? And this is very clearly non-convex. You've got this donut hole in the middle, and I can't draw 2 points on this and draw the line between, right? So this is very non-convex. And yeah, obviously the 3D version of this, it's a ball with a hollow middle, right? Okay, everyone cool with that? Okay. So how do we deal with this? So it's sort of, it's not super obvious how to convexify that, I would suggest, right? It's a little weird. So the geometry, there is a geometric way to get at this, but I find it to be extremely hard to visualize. And you have to sort of think about weird 4D geometry here. Essentially, there's a trick where you lift this up a dimension into 4D, and there you can do the convexification trick. I find that extremely hard to understand. That's what the paper does, by the way. They try drawing this like weird slices of this 4D thing to explain this that I don't find very intuitive. So I'm going to show you how to do it a different way. That's just algebraic, and then it's very simple and clear. But there is a geometric sort of, if you can think in 4 dimensions, maybe you can see the picture. I can't see the picture personally. So here's how you do it. So what we're going to do is add a new variable to the problem. We call this in optimization a slack variable, right? It's where you introduce new variables and kind of like set them equal to other things and massage the problem in weird ways. So there's a common trick in optimization. So we're going to add a new slack variable. Called gamma. And this is what they call it in the paper. That's why I'm calling it this, by the way. So go check out the paper. So this is a scalar that we're going to basically set equal to the thrust magnitude. Okay, so here's what we've got. We've got magnitude of the thrust equals this new gamma. Then we've got these other constraints we already talked about. So we've got this T min, but what we're going to do crucially here is now that I have this gamma, the T min T max thing that we drew up here, I'm going to replace that norm T with gamma. So this is all mathematically equivalent at this point. I haven't done anything to change anything. I've just introduced this new dummy variable basically. And then down here, we've got the cone constraint. So this looks like n transpose T that's an equal to gamma theta max. Cool. Everyone cool with that? All right. So I didn't change anything. I just introduced the dummy variable for that norm. So now if we go look at this again, these guys are already convex. They were before. But now what can we say about this guy? So now it's easy to see, right? What's this? Boundary of a convex constraint, right? So obviously the norm T thing there is a norm ball, and the gamma's set equal to it. So the gamma has to live on the boundary of the norm ball, right? So now it's very clear that this is the boundary of a convex set. And now you know what we're going to do, right? We're going to take that thing and turn it into an inequality. It's like a sphere constraint. So now it's easy. We play the game we just played. This number 3, that's this cone one up here, right? So it's the same thing. I moved that norm T over to the right-hand side, and I call it gamma, right? I use the dummy variable. Okay, so now we convexify. Now we just relax one. So we have, say, 1 prime or 1 star. So we take this guy and we turn it into just norm T less than or equal to gamma. And then the other stuff stays the same. Okay, now all of this is convex. Yeah, magic. So the key result in this paper, though, so we just did this. The paper kind of goes at it in a little more geometric flavor. So what you're doing here, right? You're basically like taking these constraints, and they were in R3. By introducing this gamma, you've effectively, geometrically speaking, you've lifted these things into a 4D higher dimensional space. Turns out in that higher dimensional 4D space, you can play this game, right? I think that's a little hard to think about. So I think the algebraic thing I just shared you is a little simpler and clearer, but whatever. If you check out the paper, it's cool. But the main kind of meat of the result in the paper is, yeah, I just did this. This seems fine. But if this is not tight and I go try to do this on my rocket, I'm gonna get stuff that doesn't work. That's and my rocket crashes, right? So the key result is that it turns out you can prove and they do in the paper, that for certain cost functions, and in particular, the ones they use in the paper, like minimum fuel and stuff like this, it turns out a tight convex relaxation in cases of interest. You can easily write down cases where it's not tight with the wrong kind of cost function, but if you write down the right sort of cost function, and there are a couple in there that they give as examples, one of which is minimum fuel, so that works out great. This is always tight, and they prove that in the paper. So that's the kind of the other key thing. And they do it in there. It's a little technical. You should check it out though. It's super cool. This paper is like a modern classic. Again, it was a huge deal when it came out, so it's definitely worth a read if you're at all interested in this stuff. They prove that this is tight. Using the Pontryagin minimum principle, which we talked about way at the beginning of the class, right? So you do know all of the things you need. You know all the pieces to be able to parse the paper and understand it. So it's again, it's an awesome paper. So you should check it out. There's weird drawings in there, these 4D sets that I don't quite grok, but super cool. And I think that's all I wanted to talk about today. All right. Anybody have questions about anything? All right. Now you know how to run in rockets. Pretty awesome. Yeah.
With like the gimbal, do they usually there's also have like rate control?
Yes. So there are absolutely gimbal rate constraints. It turns out that like those actuators are, yeah, I mean, they're big, right? Their bandwidth is usually sort of like 5 hertz-ish. And if you're running, like one way of getting at that is the position controller generally runs faster than that, or slower than that anyway. And then the attitude loop, I mean, you can sort of put that low pass filtering explicitly in that attitude tracking loop. So yeah, there's a few ways you can get at that. But yeah, there are absolutely bandwidth limits. Like you could, if you wanted to, if you cared, right, if it mattered, in your particular case, you could bake that into the position tracking loop by putting bounds on U dot, basically, right? Which is actually a very common move. In a lot of practical control settings, actually, with like LQR and MPC, to get at this, hacky way is you basically make your real U a state, and you make your real U dots the control, and then you can put, you know, bounds on U dot and get at these kind of rate limits on your controls. Is a very common thing to do. I don't think that you end up needing it here, but if you do need it, that's the move, and it's common. Yeah.
Explain again, how come by replacing the T normal with the gamma, it's just the same convex?
So, okay, yeah, this is like a little subtle, right? It's a tricky thing. So what I'm going to do, so here's the original stuff, right? It's all written in terms of this thrust vector. So this is a 3D vector, right? Of like really it's the force I'm applying, right? Okay, cool. So this last one is non-convex, and that's bad. Okay, so the move is right here. All I'm going to do is I'm going to introduce a new variable. So I have, you know, T, X, Y, Z components, whatever. I'm introducing a 4th decision variable gamma. So now I have 4 variables, right? I have X, Y, Z components of T, and I have this scalar gamma. So what I do right here is I just add in this first constraint. I set gamma equal to norm of T, right? So I've done really nothing. I've introduced that new variable and set it equal to norm T. And then I just replace everywhere I had norm T in the other constraints, I replace with gamma. So as that's written, it's exactly equivalent to what we had before. Nothing new, right? But the key idea now is now that number 1 is very clear that that's a boundary of a convex set. It's gamma equals norm of T. It means that gamma's got to be on the boundary of that norm ball, right, for T. So knowing that, I can play the game we just talked about where I relax to include the interior. So I just take the equal sign in number 1 and turn it into an inequality less than equals. And so now I'm including the entire interior of that ball. And so now that's convex. So that's the trick. So the trick is you introduce this new slack variable. You start out by setting it equal to norm of T. So then you have an exactly equivalent problem, right? Still non-convex. But then you can see from that number 1, that equality constraint. Now, if I just relax that equals into an less than equals, I've got a convex constraint. So now that whole set of constraints is convex. And if you're very clever and know how to use Pontryagin minimum principle and stuff, you can prove that this thing is a tight relaxation in some specific cases that matter for landing rockets with the right kind of cost. Yeah.
Do they use a linear objective function to get the boundary?
Yeah, so the standard one that they use in a lot of these cases is minimum fuel, which we kind of wrote down earlier. And so the way that shows up is fuel consumption, the rate of fuel consumption, that m dot, is a linear function of t, right? It's like minus m, or it's some constant times t, right? So it turns out that those dynamics are linear. So you kind of bootstrap on that, and it ends up being effectively a linear cost. It's the integral of a linear thing, whatever. But you can show if you work through it that minimum fuel thing ends up leading to a tight relaxation. It's a little less trivial than the one I wrote down with the pure linear objective, but it works out. And there's also a couple other ones that are also tight, and there was this was the first paper. There's a couple other ones that came later where they extended this in a few ways. They added those glide slope constraints, and they've also like showed a handful of other cost functions that still work and stuff like this. There are limitations though. Yeah, your cost function has to have some very special properties for this to work out. And so there are limits on what you can put in the cost function to have this work. Yeah.
So basically, when you're solving both T and gamma.
Yeah. T and gamma is you're adding this new decision variable to the problem. So right, exactly. So now your effective, like your decision variables is both T and gamma.
T and gamma is basically connected by that extra inequality constraint.
Yeah. Right. So yeah, it's a trivial the original version of this right up here, like that's a trivial modification of the problem, right? It's exactly mathematically equivalent to the original problem. I've just like added with that equality, right? But then what that lets me do is realize that I can relax the equality and convexify the whole thing. Okay. Yeah, that's it, guys.